I'm Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay, and I am a PMRF fellow here. Okay, so we will be discussing some questions related to lecture 5 and 6, that is week 3. Okay, let's start. Which of the, so as a first question, which of the following can be the order of an element in a group of order 16? So the question is saying that group is of order 16, so that is finite group definitely, and it has been asked what is the order of any element here. Okay, so do you have any idea how can we start, or can say?
Order of element less than or equal to order of
Sorry?
order of an element is less than or equal to
Yeah, exactly. Order of an element in a group of like it should be less than the order of the group, right? Can you explain why? Just a quick reason. Yes, you are right. Just think of why have you said that, because definitely there's something going on.
suppose
Yeah.
cyclic K is
Sorry, suppose.
cyclic of bracket of A.
Okay, generated by this, right?
Yeah.
Okay,
Yes.
yeah. So X is an element of G, and you have the group to be generated by X.
Then the order of x then any m is there in x such that x for m equal to 2. So that order of x and order of group are equal.
Yeah. Okay, so it's like if you take X raised to power 0, because this will be just x raised to power 0, x raised to power 1, like this, and then if you take this you will so there will be it cannot, if these are different, and for example let's say order of x in G is equal to, let's say whatever it is, for let's say maybe P. Okay, let's say Q better. So is this is Q, that means x raised to power Q is equal to identity. So before that, if you take x raised to power 0, 1, 2, and if you take x raised to power Q minus 1, and here comes your identity, then these elements are different. Why can you guarantee it? Because if x raised to power A is equal to x raised to power B, this implies you can just multiply by x raised to power minus b, or inverse of x raised to power b here, and you will get identity here. And now this implies a minus b is less than or equal to order of x, that is for sure, right? Because order is the least number such that x raised to power that element is equal to x raised to power, least positive integer such that the power, if you take the power you will get identity. Okay, non-negative integer actually. Now you have this condition, and what I said, positive integers only. So a minus b should be less than this. This implies if you get somewhere, for example if you get somewhere to be equal to this, then the subtraction, if you take the subtraction q minus 1 minus this power, you will get so according to this you will get identity if you take this subtraction. So, and that is for sure lesser value. So this is q minus 1 or something here, let's say q minus 5, then you will be having just 4. So q raised to power 4 is identity. So that is not true, because you have said that order is q, and q is actually okay, so q is definitely bigger than 5 because you are saying q minus 5 is valid. So basically if you have identity if you have equality anywhere, then it will lead to identity which gives a strictly lesser value than order, and which is a contradiction. So this means, yeah, so this means it cannot be possible that order of x raised to power a is equal to, it is not possible, cannot be equal to x raised to power v, where a and b are less than q, or maybe you could say equal to also, because a has to exist. So yeah, maybe just say less than q. So this is not possible. So here what do you have? If there is no equality, and definitely x raised to power 0 is equal to x raised to power q, which is identity. That means number of elements here has to be less than order of group, because if this is not true, then you have more number of elements than the order of group. So that is clear that any for any x belong to G, this set has less number of elements than G. Okay, great. Now what is the question they are asking? So for sure you know that order of, this is the order, so this is the number, order of x is less than or equal to order of G. So it is not possible, it is more than that. That means 32 is clearly not possible. Okay, now let's see what else can we do, what else can we have here. So order of an element. Okay, so here is a theorem which is from the lecture 5, that is okay, so from lecture 5, any, or maybe I'll write, we know that any subgroup of size, let's say of size S. Okay, I should introduce size of G here. We know that if G is a group of size T and H is a subgroup of size S, then S divides T. This is a theorem. So it's like if you see lecture 5, like this is the theorem written. G is a group of size T, and if you take H to be a subgroup of G, then the size of that will divide the size of group. So that is S divides T. So this is a symbol for dividing, S divides T. This means S divides T. Actually it can be proved easily, you just take cosets. So if you take G by H, and if you check, you will have like, so like this, A1H, A2H, it will end somewhere. Let's say this is N, N is the usual we could take. So you have this, and the size of these sets is actually, if you see in the normal thing, you have the size to be this, and the sizes are actually equal, and because of that you can, so because of that you have size of G. Here size of G is equal to size of H plus size of A1H, because these are the partition, this is the partition. Okay, so so these are like this, and the size of H is S, and actually sizes are same. So this will just give or this is, let's say this is G, this is the size of G is T, and this is equal to S plus up to and so on S. This is n times, so you will get T is equal to ns. That means S divides T, right? So this is actually from there. You can take a look there and you will get the, so proof is clearly written. Okay, so basically you have S divides T. Now can you interpret any element in terms of subgroup? So if you take, so what has been asked, order of an element, let's say x belong to G. So this is your element. Now order of that element has been asked. So order of element x in G, let's say this is equal to something. Again we can take, let's say S. Now what can you do with x to have a subgroup? With x, what subgroup you can take to use this theorem?
Trivial sub.
Trivial subgroup, no, with x, if you have this element, then you need to find out the order of this, so you need to have the information on the order.
Identity element.
Right, that is okay, but I'm asking with x, which subgroup
Action verse.
sorry.
Action verse.
Okay, that is element for sure. So I am asking, so you have x, now consider the subgroup this. So I am asking, you have x, then what obvious subgroup you can take to have information on x? So that is this. So this, as you have previously explained, so that is like, if you take generated by x, then that is a subgroup, right? So you have x belong to G, and now consider the subgroup. Consider the subgroup, let's say name it to be H, generated by x. What does that mean? You will just have all the powers of x, m is greater than or equal to 0. So this is the subgroup you can take always, right? Is this clear?
Then if G is cyclic, we can take that.
No, we can always take a subgroup of this kind. So so basically you have G, let's say this is your group G, sorry, you have group G. It doesn't matter what do you have in this, you just take any element of it, even identity. If you take identity, then you can have this generated by E group to be like, you will just have E, because E raised to power 2 is E raised to power 3 is E, so it is just the identity. So this is one subgroup, this is a subgroup, no doubt, because if you take for a subgroup, what should happen? Product closure it should be a group itself, like product should be there, like closure property should be satisfied, associativity should be satisfied, then identity should be there, and inverse should be there. So if you just take this element, then this set e into E is just identity, so it is there. If you take associativity, that is for sure true, because elements are from the group. So if it is okay in the group, then it is okay here also. Now third property, identity is there, e itself, and inverse should be there. So inverse of E is E, because if you multiply E and E, then you will get just E. So identity is there, sorry, inverse is there. So this is a subgroup. Now if you take just any other element, let's say A, sorry, So if you take A, then what do you have as this? This is equal to the powers of A again. So that means you will be having a raised to power 0, a raised to power 1, 2, and up to and so on. We don't care if it ends or not, but to prove a subgroup, this is a subgroup, what should we have? This is a subgroup. How can you prove that? First property, closure. For closure, what does that mean? A raised to power, let's say you have a raised to power r into a raised to power r1 or and r2. Then what will you get? r1 plus r2. That is again a power of a, and which is here, no doubt. Right?
First, we have to say that generator of A is subset of group G.
Yeah, that is true, no?
How
Because
can we prove?
okay, so so A belongs to G, right? And A belongs to G. So that means G satisfies closure property. Now if you take two elements A and A, so A into A should be there because of closure property of G.
Yes,
And again if you take A square into A, then A cube should be there. Similarly, all the powers should be there. Is that okay?
yes, yes,
Okay. So because of this, it should contain. So this generated by A should be in G. It is a subset, no doubt, because of closure property, you have all the powers. Okay. And now if you want to see if this is a subgroup, you will just check this is closure. Closure is satisfied. Associativity is definitely satisfied because these are all elements of the group G, and their associativity is satisfied. So here should be true. Now identity is definitely there because you have a raised to power 0, which is identity. And now inverse is a raised to power okay, so a raised to power something you have, and okay, a inverse should be there. And a inverse is what? A inverse is again a power. Okay, how shall I say? You are in finite group, so basically I should write m belongs to z. That is better. Actually negative powers are also there. If you are in finite group, you don't need to care because a inverse is itself some power of a. Because if it is finite, if this is finite, then a raised to power m is equal to identity for some m. That means you can write m minus 1 into a. Then this is your inverse that exists here. So that is again a positive power. So if you want to see in infinite group, it should be there. It should be like m belongs to z to have the inverse. So as I did a mistake here, I can correct it from the thing that inverse should be there. So inverse should be there. That means a raised to power minus 1 should be there. So yeah, is it clear why this
yes,
is a subgroup? Okay.
yes.
So let's come to our thing. Yeah. So you have the condition to be, so A belongs to G and you have this set. Okay, better to write again M belongs to Z. This is integer set. Okay, now you have this. Okay, where were we? Yeah, we can actually remove this. So you have such type of subgroups always, and you can make use of it. Okay, so M belongs to Z. Now this is your subgroup, and if you take this now and what will be the cardinality of this set? Can you tell me? What will be order of size of H? Yes. So what elements do you have? So size of this set, what does that mean? You have just you need to count the elements. So it's like you have x raised to power 0, x raised to power 1, x raised to power 2, and actually we are in finite group. So okay, I can write it. Yeah, if G is a finite group. Okay, So obviously we have like order 16 they have asked, so that means we need to discuss about just finite groups. So let's say it will end somewhere, uh, so that is x raised to power, okay, I have used m here, so let's say this is m0 or something. So, and that is your, okay, have I, okay, I assumed what is order is s, so I can use it. So if you see, this is what, this is the order means this is identity, and here this is identity, so this is, these are same elements, same. So if you count what it will be, so you can start by counting from here 1 2, and after this if you take x raised to power s plus 1, what will you get? You will get x raised to power s, yeah, yes. So this is,
X.
yeah, so this is again repeated, these are, this is these are same. So basically you will be in this loop, like you will get this and then again this. So basically so what will be the count here, if the, in the set, what are the distinct elements here?
Yes.
Sorry, how many?
Yes.
S,
Yes.
yeah, exactly. And that is what, that is order of that element. So this is always true. So if you have, so just in finite groups right now, because in infinite groups it could be infinite, finite groups, and even in infinite group it's just the count, and that is exactly the order, because after that you will get all the elements repeated. So in finite groups, order of yes, size of this set, if x belongs to G, then size of this set is equal to order of this element. So that is always true. So now we may use the fact, this fact. So it says if you have a subgroup, that is H you have, then, and G is your group, then the, then we have order, sorry, what is that, yes, order of H should divide order of G, that is exactly order, no, this is size, sorry. So size of group divides size of subgroup divides the size of group. Now what is the size is equal to order of G of X, because H is this, and this should divide order of G, that is 16. So order of any element should divide the size of G, okay. So that means what are the possibilities? So order could be either 0,
Brackets of 16.
yeah, yeah, factors of 16, or maybe you can say divisors of 16. So that is 0 1, sorry, not 0, sorry, you have 1 1 2 4 8 16. So in your question, what can you say now? You have just one option here, 8, because 15 and 14 are not true. Okay. Okay, if you have any question, feel free to ask. Yeah. Okay, as a solution, let's come to second question. Consider two groups G1 and G2 and choose the correct statement. Okay, let's see what do we have. G1 and G2 are so it has been asked what can you say about G1 and G2? So are they isomorphic, about the order, or just this? Okay. So G1 is given to be Z6 and G2 is Z2 cross Z3. Okay. So can you tell me? Actually, this has been done in the last lecture, kind of. Is it isomorphic or not? Okay, let's see. Yeah. Okay. So again, I can use a theorem. So that is, if you see the lecture notes, so lecture 5 from lecture 5 is just so from structure theorem. So this is a structure theorem for cyclic groups. So actually it has been discussed only for cyclic group. There it is, so it says from structure theorem for cyclic groups, we know that any group, again so it is cyclic group, that means it is commutative, and we are also talking about finite groups, finite cyclic groups. We know that any group G is isomorphic, or first we know that if G is a group of order, of size, it's just, if that is a group, we will say size, of size n is equal to p1 raised to power n1, p2 raised to power n2, up to and so on, pm raised to power nm. So basically you will just write distinct factors, so of size n, where p1, p2, up to and so on, pm are distinct primes. So you just do prime factorization, are distinct primes. Then G is isomorphic to Z P1 N1 cross Z P2 N2 cross up to and so on Z Pm Nm. So basically what this says, you just write n as the product of n as product of primes. So it's like, for example, you have 8, then you will write 2 raised to power 3. Okay, here you will write 2 raised to power 3. If you have, for example, 6, you will write 2 into 3. So power is just 1. So it's like this. You are just doing the prime factorization. Write it in this form. Then G is isomorphic to product of cyclic groups. Okay. So this is the theorem. This is the structure theorem. So what can you conclude here using this theorem? So this is actually saying about all the finite cyclic groups. You can write all the finite cyclic groups in this form. Actually there is one more thing. You can actually write G to be this. So if you see G is a cyclic group of size n, then you can actually write it as in the form of it is isomorphic to Zn. That is also true. So okay, in the next part I will okay, next question is this. Okay, I will actually write a structure theorem for finite abelian groups. That is actually more important to know. Okay, so basically here what does that mean? Okay, actually structure, okay, it's fine. So you have this thing. So because of this, what could you say here? Z6 is isomorphic to, you can write 6 to be 2 into 3, right? So Z6 is isomorphic to
Z2 into Z.
Exactly. So from this theorem you can actually say these are isomorphic. So if you have 4 is equal to 2 into 2, actually you cannot say, because according to this theorem, actually from this theorem you cannot say, at least, and then you can actually prove that you cannot split more. You cannot split more. If you split more, it might be so what shall I say, it might not be cyclic. Okay, so just understand this. If you have cyclic group, you can actually split it in this form, and that is the maximum split you can do. Maximum maximum number of parts in this product you could have. Okay, this is maximum. like this count is maximum. You can swap between any of these two, but count should be maximum this, or you can actually write it in lesser, like z p1 raised to power, for example z6, you can write it in one form, and this is second form also. So this is the maximum split you can do. Okay, so according to this, A option is correct. Let's see other options are correct or not. Order of both groups is not same. Can you tell me? So order of this group is
6.
6, and order of this group is
6.
6, right? So you have 2 elements here, you have 3 elements here, that should be 6. Actually these are isomorphic and these are finite groups. You can always go with like the count should be same. Okay, great. Let's come to, so basically B is not, C is not correct because these are isomorphic, and obviously not D. Okay. Let P1 and P2 be distinct primes. Up to isomorphism, how many finite abelian groups are there of order P1 raised to power 4 and P2 raised to power 4? So, okay, here I will introduce the structure theorem of abelian groups, finite abelian groups. I'll just write what it is, okay. So, what has been asked, that is important first. So, they are asking, let P1 and P2 be distinct primes. Up to isomorphism, how many finite abelian groups you can have of this order? So, you have the size, you know groups should be of size P1 raised to power 4 and P2 raised to power 4. So can you tell us like how many groups, how many distinct groups, different groups you could have, but these should not be isomorphic. So for example, if you say Z6 is there and Z2 cross Z3 is there, you cannot say like these are different, because up to isomorphism this is just one. Up to isomorphism means like if these are isomorphic, we will count it as one. So Z6 and Z2 cross Z3 is just one in this count. Okay. Sorry for this disturbance. I cannot do this just. Okay, so you have order of G is this. Now these type of things will be counted as one. So that means, and you are talking about just abelian groups. Okay. So I'll just write what is the structure theorem for abelian groups, that is important. So you need to count how many of this order groups you could find up to isomorphism. Okay, yeah. Yeah. So by structure theorem, for finite abelian groups. So we are just talking about finite groups, and these are abelian also. So we have commutativity. We know that if G is a group of order let's say n, you which is equal to, let's say, p1 raised, similar to the previous discussion, pm raised to power nm, it's just the product of order n is equal to p1 raised to power n1, p2 raised to power n2, up to and so on, pm raised to power nm. Just write it as the do the prime decomposition, prime factorization, sorry. Then G is a group of order this, where P1, I am not saying these are distinct, P1, P2 up to and so on, PM, right, are just primes. I am not writing these are distinct primes or whatever, are primes, prime integers. It is possible that P1 is equal to P2, okay, prime integers. Then G is isomorphic to Z P1 raised to power n1 cross z p2 raised to power n2. You have things like that. The important thing is to understand these are just prime integers, not necessarily distinct. Not necessarily distinct. Okay, it is not important that these are distinct. Now what is the main thing? Yeah. Now what will help here, like g is equal to this, and so okay, for example, let's say you have 12. So let's say n is equal to 12, so order of g is equal to 12. What will be the prime factorization?
2 square into 3.
Yeah, 2 square into 3. So here we are saying we can actually think of 2 into 2 into 3. We could think of like this, and from this, if you take this consideration, you will have z. uh, okay, one thing, sorry, I did a mistake. G is a group of order this, where these are prime integers. Then okay, I should write it like this. This is a wrong way. G is a group of order n. You just say order n. Okay, I'll explain why I am changing it. I am just writing in some different form. G is a group of order n, and obviously there is no where here. Yeah. So you have G is a group of order n, and then G can be written as z p1 raised to power n1, z p2 raised to power n2. G is isomorphic to nn. Sorry, nm. Okay. Then G is isomorphic to this thing, where p1, p2 up to and so on, pm are prime numbers or prime integers dividing and again not necessarily distinct. Are prime numbers dividing n and n1 up to and so on, nm are non-negative integers. Okay, so okay, what does that mean? That is important, or actually, yeah, that's okay. So yeah, what is important here to note, that we are just saying you just pick any group which is abelian, which is finite abelian group, then you can actually write it as a product of cyclic groups. You are saying so this is the other statement if you want to write, that is okay, I'll just change a color. Other statement, simpler statement, any finite abelian group G is a product of finite cyclic groups. So basically it is saying, like, if you have any abelian group, then you can actually write it as a product of finite cyclic groups. If you see here, all are cyclic groups, okay, and these are fine. And if any finite cyclic, what is the definition of cyclic group? If you see from the lectures, the definition of cyclic group is cyclic group is isomorphic, a group which is isomorphic to Zn, then it is a cyclic group. Isomorphic to Zn, it is isomorphic to Zn. right? Are you familiar with it? Are you with me?
Yes, ma'am.
Okay. uh, I hope disturbance cannot do anything. Okay, any finite. So this is isomorphic to Zn, so that's why this is coming into picture. So basically, it is characterizing all the finite abelian groups. There is no any group which cannot be isomorphic to this part, this type of thing. Okay, so that's why it is saying it has been said that this is a structured theorem. So a structured theorem, that means it characterizes all the finite abelian groups. And because of this, what do you have? Because of this, if you see, if you now you have order of group to be, so order of group is given to be what is it, p1 raised to power p1 raised to power 4 and p2 raised to power 4, and where p1 and p2 are prime numbers, are distinct primes. So it is important to note that these are distinct primes. Okay, otherwise it could be isomorphic in something. Okay, now now because of these two theorems, if you see, because of these two structure theorems, we can actually characterize all the abelian groups here up to isomorphism. So can you suggest what all the possibilities you can take? So possibilities are coming from, like for example, if you have Z4, you could also have Z2 cross Z2 of order 4. So if you have order to be order of G, so you have order of G to be 4, then you could have Z4, you could have Z2 cross Z2, and these are only two possibilities. It's like that. So can you tell me what are all the options you could have?
ZP1 cross ZP1 cross ZP1 cross
Yeah,
ZP1.
very good. ZP1 cross ZP1 cross ZP1 cross ZP1, and
ZP2 cross
okay, 4 times, right?
4
Or power 4 or times 4?
into 4.
Uh,
ZP2 ZP2 Z.
Okay, 4 times. So can I write it like this? This means ZP2 cross ZP2 4 times. Okay, so it's just a way of writing. So basically you have, as at first, as you said, you just take 4 times and you just take this to be 4 times. Okay, second option, what could you take? Yes, now what can you do? Yeah. Yes, Shanari?
ZP1 square whole square.
Yeah, right.
No. ZP1 square.
Okay. So basically, what are you doing exactly? You are just taking all the possible options for 4. So basically, what you are doing? You are partitioning 4 and considering all the options. So it's like, for 4, what could you have? So at this place, what could you have? You can have 4. You can have 3 plus 1. You can have 2 plus 2. You can have 1 plus 3. Yeah, again 1 plus 3 is different, is same, because if you have zp1 into zp2, and if you have then this is isomorphic to zp2 cross zp1, because what isomorphism can you take? You just take ab to ba. So this is an isomorphism. So you just consider all the partitions. So 3 plus 1, 2 plus, yeah.
First and second are same. ZP1 square. ZP1 square is different.
Sorry, come again.
Z in subscript P1 square.
This one, right?
In subscript, instead of P1, we
Hmm.
should write P1 square.
Okay, P1 is square, you are saying. Okay,
Uh,
okay. Yeah, exactly. Yeah, exactly. Yeah, this is same. Thank you. Yes, so it is like writing again. Exactly. So you have P1 square, and here you can take P1 raised to power. Yeah, better to write it in the expanded form. Even I am confused. So yeah, you have this. So yeah, you can take p1 square, and you can again take square of this, like parts. So basically what you are doing, you are taking you are doing, so you have 4. So yeah, I would say I should write it in this form. So you have this first one. Okay, let it be. Yeah. Yes. So what you are doing, you are just thinking what powers you could take. Okay. So you have 4. So either you can have power like, okay. So basically this is 1 plus 1 plus 1 plus 1, and you have 2 plus 1 plus 1, and anything else. These 5, right? You have these type of partitions with you. So this implies you have z p1 raised to power 4. This implies you have z p1 raised to power 3 into z p1 raised to power 1. Here you have z p2, sorry, p1 raised to power 2, and you have z p2 p1 raised to power 2. This implies z p1 cross z p1 cross z p1 cross z p1, and this implies z p1 square cross z p1 cross z p1. Is that okay? All the options you are having here.
Yes.
Okay, so these are all the options which is possible, and you have same thing for this also. So basically what do you have? So the partition of 4, that is what do you have? 1 2 3 4 5, and the other side what do you have? So you have 5 options with this, and again with this also you have 5 options. So 5 cross 5, because with any of this you can take all the 5 options with z5, right? All these will be different. So 5 cross 5, that is 25. So it should be 20. Oh, okay, what have I missed? uh, let's see, these are same, yeah. No, it should be 25. There is no option like this, so it should be 25. So this is correct. Because, so one more thing to note it down. So here if you observe, we have taken this to be different. So this to be different from this. So it's like z. So okay, in a simpler form, if I say p1 raised to power alpha, then this is not isomorphic to p1 raised to power alpha 1 cross p2 raised to power alpha 2, where alpha 1 and plus alpha 2, okay, alpha 1 and alpha 2 are greater than 0, bigger than 0, that is important, and alpha 1 plus alpha 2 is equal to alpha. So basically we are saying, for example, you cannot write this is not isomorphic to z2 cross z2. If you remember, we have explained this. I gave a proof of this thing. So exactly in the same way you can actually prove this. So keep it as an exercise. If you like, if you have doubt in this, we can discuss next time. So you can actually exactly follow the proof of this. You just take any element here and map it to a comma b. So for any element means you just take identity and map it to some a comma b and prove it. This is not possible. So you cannot have an isomorphism between these two. Will you do it?
Yes.
Okay. So very good. Just this is very important. This is important because if this is true, that means these are all different. Because what have you done? You have actually splitted here. You have actually splitted 3 into 2 plus 1, right? And actually if you see, actually I can write it in a better form, like 2 plus 2, and then write 2 plus 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So all these are different. So these are different. That's why the count is exactly 25. Okay? Is it clear?
Yes.
Okay. Okay, let's move to next question. Suppose every proper subgroup H of a group G is cyclic. Which one of the following statements is true? Okay, let's see what you have. Okay, suppose every proper subgroup. So H is given to be, H is a subgroup and it is given it is a subgroup of G. This is a notation of subgroup. Usually subset is this, and for subgroup we actually write this less than term. This is for subgroup of G. Okay, so it is given that every proper subgroups. So this is a proper subgroup, and these are all cyclic. Like if you take any subgroup, proper subgroups are cyclic. Then which of the following statement is true? Okay, let's see. Firstly, tell me. Just take an example. So for an
What
example,
is mean by proper subgroup?
sorry.
Proper subgroup means
Okay, proper means no non-trivial. We are asking for. Okay, proper means H is not equal to G. So that means all subgroups, or maybe I'll just say any subgroup H is said to be proper, said to be a proper subgroup if H is not equal to G. So this should not be the whole group. Okay, so proper means exactly a lesser number of elements than G. Okay, okay. Yeah, so let's take an example. So basically it is asking, so if it says like if it does not say proper, it just says subgroups of G. So G itself a subgroup of G, because G is a group and it is contained in G, so G is itself is a subgroup, so that means G is itself cyclic. So that question doesn't matter. Like this is, you are saying just G is a subgroup, G is cyclic. So proper is important here. So okay, let's take examples. So firstly, if you take any cyclic group, the subgroup will be cyclic. Now you just, okay, I'm taking an example. Let's take Z2 cross Z2. So that is a common example. If you see here, what are the subgroups of this group? Okay, are you familiar with Klein 4 group?
no more.
Okay, so this is actually isomorphic to Klein 4 group, and this is just okay, I'll explain what this is. So just to remember, this is Klein 4 group, so I'm not going into this. So basically I'm saying this will give you an counter example. Firstly, tell me, is this a cyclic group?
Yes.
Yes, Z2 cross Z2. Okay,
Z2 is cyclic.
yeah, Z2 itself is cyclic, but you are taking the product Z2 cross Z2. Is it cyclic?
Don't.
Okay, so why it is not? Actually, you have proved this. Z4 is not isomorphic to Z2 cross Z2. So cyclic subgroups. So first and all, if this is like, if okay, Zm cross Zn. So okay, I will write again. So this is again, so this is coming from all these theorems again. If M and N are co-prime, then okay, we have to say something. Yeah, Zmn is isomorphic to Zm cross Zn. So this is only true when you have GCD to be GCD of M and N should be 1. Was it in a tutorial, I guess? What was it? Okay, just there was a, I guess, assignment 1, or okay, 1 second. not this. Yeah, V2, I don't know. Yeah, this one. So, okay, generator of Zn should be, okay, let's not go to this. Yeah, yes. So you have, if M and N are co-prime, then Zmn is isomorphic to Zm cross Zn. This is true. And if M and N, if GCD of M and N is not equal to 1, then Zmn is not isomorphic to Zm cross Zn. This is in general true. Why? Actually, you can prove this. This has the same proof as of Z4 is not isomorphic to Z2 cross Z2. What do you what will you do? Zmn. So this is the theorem you can always learn and remember. So okay, this is coming from, again, so this is again coming from this. Okay, no. Okay, Zmn is not isomorphic to Zm cross Zn. To prove this, what do you say? You say these are isomorphic, then one should map to a comma b, and then what can you do? You can actually have an element. Yeah, so GCD should be important at this place, because if GCD is D, okay, I'm not proving it, you just do it using this, okay, just okay, I'm right, because it will take time. You can actually prove it using this, just follow the same trick as in this proof that is coming from week 2, I guess. Okay, so yeah, if M and N are co-prime, then these are isomorphic. If and that means co-prime means GCD is 1, and if GCD is not 1, then definitely you cannot write Zmn to be isomorphic to Zm cross Zn. To prove this, use this trick. Okay, and if you're not able to, you can ask me next time, but you will be easily figure it out using this proof. Okay, yeah, so basically, where am I going? Z2 cross Z2, this is not cyclic, because if it is cyclic, then it has to be, okay, yeah, if it is cyclic, then it has to be, so okay, any cyclic group, the definition of cyclic group is what? Okay, if you remember the definition of cyclic group.
For x belongs to G, then Nx
Yeah.
belongs
Okay, cyclic group definition, right? I am using this definition which is from the lectures, so where cyclic group has been first mentioned. So G is a cyclic group if G is isomorphic to Zn. This is G is cyclic group of order n. Okay, order means size, of order n if G is isomorphic to Zn. If you know G is isomorphic to Zn, then that is cyclic. Okay, that is the first theorem if you see in the lectures, and because of this you can prove the lemma that it has one generator. That means G is generated by X. Okay, so here cyclic group has been introduced, and because of this, if you see and you know Z4 M cross N, or you may say this one, yeah, so for example, this is this theorem, if you prove this theorem, you can actually proving this also, because P1 raised to power alpha 1 and P2 raised to power alpha 2 has GCD in terms of P1, not 1. Okay, so that's why you can, if you prove this, you can actually proving this part also. Okay, according to this, Z4 is not isomorphic to Z2 cross Z2 because 2 and 2 has GCD 2, so that is not 1, so that means this is true, this is not. So Z4 is not isomorphic to Z2 cross Z2. And now because of this is not cyclic. Now I am saying this is a good example to think about our question. It is saying all the proper subgroups of G is cyclic. So let's see what are the subgroups of Z2 cross Z2. Means proper subgroup means you are not taking a 4 order group. Okay, now can you tell me what will be the order of its subgroups? Size of the subgroup, what can you say from the first question? If you have H,
Divides.
yeah, order of H should divide order of G. Very good. So order of, so you are saying this is 4, then what are the possibilities for H? It could be 1, 2 and 4, exactly. And 4 you are not taking because full group you are not allowed to take, you are just taking proper subgroups. So proper subgroups you have just two options, and with one you always have just the identity one, because not any element cannot be if this is not identity, then this is not a subgroup. Not a subgroup. Why? Because identity should always be there, and if this is not identity, then you have to put identity to make it a group. So for with order 1 you have just one subgroup. Okay, now let's come to the two order subgroups. So two order subgroups, uh, okay, for no confusion just write subgroups of order 2. Subgroups of order 2. Okay, so you have subgroups of order 2. You need you now let's see what are the subgroups you can take. Okay, what are the elements of Z2 cross Z2? This is 0 0 0 1 1 0 and 1 1, right? You have just this, these are like with bar. Okay, you are having mod 2 mod 2 for both of this. Is that okay? Or 4 elements we have this,
Yes.
and this is identity, so this is your identity element. Now okay, tell me if you take this, let's see, if you take 0 comma 1. Okay, forget about the theorems we have taken, just think here. If you take 0 comma 1, then what do you need? If you want to find out the subgroups, and you are saying all the subgroups can have order 2, so just pick any element. Let's see what elements you could have here. So 0 1, and now square of this element, so that means 0 1 plus 0 1 again. So that means 0 plus 1 plus 1, that is 2 bar, that is 0, right? Is that
Yes.
okay? So you have 0 0 again. So order of this element is 2. So that means you can take this subgroup. So this is one subgroup you can take. So let's say H1. Similarly, if you take other subgroup, you can have H2 to be 1 0 and again 0 0, because if you sum it up you will get 1 plus 1 0 plus 0. 1 plus 1 is 2, that is 0, so you will again get 0 0. And H3, if you take this subgroup 1 comma 1, then you will have if you sum it up again, 1 plus 1 1
0
plus 1
comma 0.
0 comma 0. So if you take just one element you will get these three. Now let's see if you take two elements, what will you get in one group? You can do that, right? Is it possible? You are taking subgroups, so you should have all the possibilities for subgroups. So if you take, for example, if you take two elements, so first of actually you are done with this, because if you take any two elements, so identity should be there, so identity is there. Now if you take any other element, then all these three are there. You cannot take any third element because subgroups have order 2, right? You have no subgroup of order 3 because that is not possible. Actually that is not possible, you can check it here. because if you take 0 comma 1 and if you take 1 comma 0 here, then you will have to have the sum because of closure property. Then because of sum you will get 1 plus 1, right? Sorry, if you sum these two elements, 0 plus 1 1, 1 plus 0 is 1. So so third element will be there and identity you need to put. So this is this. Is it clear?
Yes,
So
ma'am.
you have just four subgroups. So this is okay, if you take h1 h2 h3 and this is h4, so you have just four subgroups, proper subgroups. Okay, now obviously these are all cyclic because these are generated by this element. If you see, these are generated by just this element, and like this is generated by 1 comma 1. Generated by means, okay, sorry, I should not go like this. If you see this definition as we were discussing, G should be isomorphic to Z, Zn. So this is isomorphic to Z2 because these are just two elements. This is like 0, this is like 1. Okay, so lemma says G is isomorphic to group generated by 1. So here if you see, it is generated by 1 comma 1, it is generated by 1 0 because we have made it like this. If you see, we have just taking the sum, square of this you get the identity, square of this you get the identity. So it is generated by these. So h1 is generated by this element, h2 is generated by this element, h3 is generated by 1 comma 1. So both the definition, if you see, you can think of it. So is it clear? These are all cyclic. Again, obviously this is cyclic, generated by identity. Is that okay?
Yes.
Okay. So we have this condition right now. Uh, but the one thing we have now, this is not cyclic, but all the proper subgroups are cyclic. Proper subgroups are cyclic. You have this condition now, proper subgroups are cyclic, and any of the this itself is not cyclic. So because of that, what can you say? G may not be cyclic. Second is definitely wrong. G must be an abelian group. Okay, so for this actually you are dealing with commutative groups. So okay, I will just say this is not true. For that, you have not reached on this. So let's skip this part. If you want to know the examples, I can write that is D3 or S3. So these are not, you are not familiar with these dihedral group and dihedral group, and this is symmetric group of this is symmetric group. You're not familiar with this, right?
Yes.
Okay, so just skip this option, for example. But if you want to know, this is not true because these are non-commutative groups. If you are curious, you can search it about these two groups, non-commutative groups, and this one exactly with 6 elements, you can have your example. Okay. Okay, G must be a product of two cyclic groups. So must be doesn't make any sense because you can take G is equal to Zn, which is isomorphic. So if you take, for example, Z4, so two cyclic groups, it is saying, so Z4, actually if you think of identity, it doesn't make any sense. So like E cross Z4, if you can think of, but you can, in that sense, you can write it as E cross E cross E cross E. So this doesn't make any sense. So because Z2 cross Z2, again you can write it in two cyclic groups, no non-identity cyclic groups, you could say that. So it should be clear. So this is not true. Okay, let's come to the next question. This is important because I guess this will help in the assignment also. Okay. Okay, the number of distinct colorings, sorry, not solutions, yeah, oh, Sorry. Okay, so what does this question say? The number of distinct colorings of the corners of a square using 37 colors. So actually this is exactly, if you see the lecture 6, you will know how to do this. So here this is a very good application for groups to study abstractness. So okay, so for example, if you have just a square, or you have just four corners, square I'm talking about. So if you have four corners and you want to color these corners, for example using black and white, for example, number of distinct colorings of the corners of a square using, oh, okay, yeah, so you have a square, and now it has been asked you have 37 colors. Okay, yeah, you have 37 colors. Is it the question which need to be asked? mm. Okay, if this is the question, actually this is not the question for sure. Because if you need to see that, you can easily see that, because so for example, if you have just two colors, okay, two colors, let's say black and white. Okay, I'll just correct it. Okay, this is not the question. uh, yeah, so number of okay, I'll write it. The number of
I think it
distinct,
is polygon
sorry,
of 37 corners.
yeah, exactly, the number of distinct ways to color, uh, yeah, oh you are, yes, color, um, distinct ways to color. You have color black and white, two colors to color, polygon, regular polygon again. Okay, so it's like same side, regular polygon of 37 sides. So, or maybe you can say corners, both is same. Corners, yeah, this is actually the question which makes sense. You can actually find out with this 37 thing if you want to see the question. So it's like a square, you have 37 options for this, 37 options, 37 options, 37 options, and you can rotate it. So let's say you have black here, black here, black here, black here, then if you rotate it, if that will be same, like this will be the same, and then if you say this is white, you have 37 options for color. So you can actually count it by hand. Okay, because a square is a very small figure to think about. The main thing is you have a bigger polygon which has 37 corners. Even it is very hard to think of it. So if you see the lectures, that is very explained way to think of this. Okay, so I am going with the notations of the lectures, and because of this, actually I can write Burnside theorem. So have you seen this lecture?
Madam, can you explain that theorem? I didn't understand that.
Okay. I am just explaining. I'll not go into the proof because that is that will be hard for me because of time. But yeah, so Burnside theorem. What does this say? This says that if, okay, I will explain what are the notations, so that will help you. Okay, first I am writing, so number of equivalence class, should I say? Okay, equivalence class. Okay, shall I write? Okay, number of I'll explain. 1 mod g summation pi belongs to g, and you have x pi. Okay, so what are these notations? I'll explain. So firstly, what is g? G is the group with all the rotations. So you have pi 0, pi 1, pi 2, you have pi 36. So what are these? So pi I is actually is a map which sends I which sends j to I plus j. So what does that mean exactly? So you have a polygon, let's say 1 2, I'm explaining in a hexagon so that you will understand better. Okay, if you will not follow, just unmute and speak. So you have this 1 2 3 4 5 6. Okay, so it is mapping to, okay, figure is same. So 1 goes to 2. So what it is doing, it is rotating. Okay, so 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes to 1. So it is like modulo 6. So modulo 6, sorry, we have 37.
Then that is not the solution.
Sorry,
If we 2 goes to one first position, then
no.
upper gate is the flat position.
Come again. What are you saying?
If 2 goes to the position of 1, then upper position will be flat position. Then that rotation was different than first rotation.
If you are taking 2 goes to 1, then what? Acha,
Upper,
okay, you are saying in this situation, if you take just 2 goes to 1 and everything else is same, right?
yes.
So we are not taking such kind of maps. We are just taking rotations. Rotations means order should be same, like 1 2 3 4 5 6 7 should be in this form. I will just say this map. This map, only this map means you are just adding it up. So 1 goes to 2, 2 goes to 3. There is an order in this. So j goes to 1 plus j, that is like you have rotating once. Okay, and then you are getting all the maps. Like pi 2 will be like 1 goes to 3. So it will start like not here, it will start like 1 goes to 3, that means 3, 2 goes to 4, you are adding just 2. So 4 5 6 1 2. So order will be like this, just you are rotating it up. And what you are suggesting, 2 goes to 1, we are not thinking of that. We are not taking such kind of maps. We are just taking, because the main thing is you are coloring it. Okay, so in color, what will be the same thing? We are actually thinking in a way that it will remain the same thing, because you are able to rotate the figure, right? If you have, for example, let's say you have a square and you have here black, white. So, and now you have the other one, you have hair black and white. So these are counted as the same figures, because so you have a thing, you have a square, let's say in 3 dimensional, you have in your hand this square, and you can actually rotate it. You can rotate it, then white color, this black color will come here. So this is the same thing, because figure is same. So this is counted as the same figure in coloring. Okay, so distinct ways means these are considered as the same figures. Okay, so question has started like this. Now you have taken, because of this you are only considering rotations. If you just think of, like, if you just okay, here you cannot say that. For example, if you have hair black, okay, and now what you will do, you will just do hair black, and you will just flip these two. then what will you get? Here again black is there. Okay, so this you have. Okay, now if you see, can you rotate it and get the same figure? Like, are they same? Here you have at the same side, you have black color. Here you have different at different corners. Okay, you cannot make it like, you whatever you do with the figure, you cannot get it. Okay, one more thing, if you just think of okay, we are not thinking about reflections also. For example, if you see black, you will just so basically you have a square, and if you rotate it, for example, you have a board. Okay, um, a square board. Okay, but backside is not a board. Backside is just like a wooden thing, and in front you have whiteboard. So you cannot actually reflect it. So you are not considering this reflection. Okay, this is reflection. And rotation is just like, you can move it in, so basically you can move it in the same plane, like you are just like staring, you are just rotating it. Okay, so in that situation, only in that situation, what are all the possibilities for coloring? What are the distinct possibilities for coloring? So that is your question. Because of that, we are just considering rotations in this set. Okay, is it clear? Okay, so so that is your set. G is actually the all the rotations which are possible. Now this is saying, and what is x pi? So equivalence class is like I will write number of distinct ways to color, because I am not introducing what are equivalence class here. So distinct ways to color, that is equal to one mod this. And now what is x pi? This is also we can get rid of for now. Yeah, so what is x pi? So let's see. Okay, what is x pi? X pi is all the elements a in what should be, okay, let's see what do we have. A goes to a, and a is your set. Okay, that I need to explain. So what is x here, where x is equal to, now it is saying all the possible all the possible polygons with color, with colors. Okay, what does that mean? All the ways in which we can color the polygon. So what does that mean? This is a set of polygons with colors. Okay, so it is not saying rotating or something. We are not saying distinct, we are just thinking all the polygons which are possible with in color. Okay, so what does that mean? This means you have a polygon, for example this. Now you have two options for this, two options for this, two options for this, options to color. Okay, you are saying black and white. Okay, so you can color either black or white, either black or white, either black or white. So you are saying there are two options for every position. So it's like what so how many, so this set is not saying you are, so why we are saying equivalence class? The general set we have is like all the possibilities we have. Now we are not saying if we rotate it that is different, if we rotate it that is not different. We are not thinking of that. We are just saying if you rotate it you will get a different one. So not even thinking of rotation, it's just taking all the possibilities which is possible if we color it. So this is like 2 cross 2 cross 2 cross 2. So in this situation we are just saying if you color here black, here white, 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 and here if you have black here, white, these are different in the set X, different in set X. Is that clear? What is this set?
Yes.
Okay, so that is your question. If the question has been asked like just find all the possibilities of coloring in this situation, and rotation is not same, or like this kind of thing, if they have asked this, then you can directly say 2 raised to power whatever number of corners it has been given, that is 2 raised to power 37. But the condition they have imposed, if that is your question, you can directly say there is no need of group, there is nothing which is required. But the question says if you rotate it sorry, if you rotate it you will get a if you rotate it you will get the same one. Like if for example, if this is a square, it will be identical if you rotate it and you have the same coloring in that place. Okay, so that is your relation given. So it's like a real time question. Is it clear what is the question, and what is this set X?
Yes.
Okay, very good. So X is this. So that means number of elements of this X are like for example, you have this big gun, so like a polygon, and you have polygon P1, polygon P1, polygon P2. These are all the possible colorings. Okay, these are polygons. So set is the collection of all the polygons with color. Okay, and you will be having how many? This will be p2 raised to power 37, because all the possibilities are two options for this, two options for this. That is 2 raised to power 37, right? So cardinality of this set X is 2 raised to power 37. Now come to your question. So Burnside theorem, if you just think of what is the theorem, what are all the important things you need to remember for this theorem, like what is G, what is your X, what is Xg. So Xg is saying all the elements of this X. So can I better write? Okay, so I am writing P, like P means polygon. Okay, so pi of P, if you take this polygon, you will get the same polygon. Like if you map the polygon, you will get the same polygon. Can you okay, so let's see what are all the options. And pi is like your rotation. Okay, sorry, this one. Okay, so you have pi 1. So you need to calculate, so according to formula you have what you need to find out, this sorry, what was it, order of G. Yeah, so order of G, summation x pi, and pi belongs to X. Okay, so order of G, you know what is it? 37, because G is all the set of all the rotations, that is 37. And summation pi belongs to X, and X pi is, you need to calculate. Okay, let's calculate it. So this is, what is this? This is the sum of X pi 1, sorry, pi 0, it starts with pi 0, X pi 1 plus up to and so on X pi 36, because all are these oh sorry, this is not X, this is G. Okay, the rotations are from G. Okay, so this set you need to find out. So let's see what we have. So we need to find out these values. Okay, so what is this? This is equal to all the P, like P the polygon in the coloring set, such that pi 0 of P is equal to P. Like if you map this polygon, you will get the same polygon. What does that mean? And what is pi 0? Pi 0 means I goes to I plus Z, sorry, I we are using for, so I should write J goes to J plus I. Okay, have I write it correctly? Yeah, J goes to I plus J. Okay, so this is pi I. Pi I means this. Yes, pi I means this j goes to j plus I. So what does that mean? You are saying j could be, j is your polygon numbers 1, 2, 3, 4. So 1 goes to 1 plus 0. So it is pi 0 is exactly identity. You are sending this polygon to the same exact polygon. You are not rotating anything, right? So pi 0 is so if you take any polygon in this set of polygons with color, so you have colored in every possible way, and if you take any polygon, if you use pi 0, apply pi 0 to it, then it will be the same, because pi 0 is not doing anything, it is just making it identity. So with this condition, you are taking all the polygons which satisfy this property with pi 0. So is it true? So what will be the set count? What will be the number of elements? So this is the set of all the polygons with color, okay, and which satisfy this property. And if you see, pi 0 is not doing anything, so it is making same polygon to same polygon. So we can say all the polygons are here. So the set is exactly X. Can you tell, can you say it? So this is X, exactly X. All the polygons are here. Is it clear or not? I can explain it again, don't worry.
Yes.
Okay. So you have full set. So basically pi this is equal to, just think of it, you just need to take all the polygons which maps P to P, like which maps when you apply pi 0, you get the same polygon, and pi 0 is identity, it is not rotating at all, it is not doing anything, so polygon will map to the same polygon. Okay, so this is equal to 2 raised to power 37. The set X is 2 raised to power 37, all the possibilities. Now, what will be pi 1? Okay, pi 1 is again, I'm writing the set again. P, all the polygons P, such that pi 1 of P is equal to P. Question is same, like it is saying the polygon should map to itself under this pi 1. But what pi 1 is doing? Pi 1 is doing, it is mapping plus 1, like 1 will go to 2, 2 will go to 3, it is just rotating by 1. So it's like j goes to, so pi 1, the map is j goes to I plus j. It is just add this, so that is 1. So 1 plus j, it is, so 2 goes to 3, 3 goes to 4. So if you have this figure 1, 2, 3, 4, 5, 6, and if you take this, here you will get 1 goes to 2, 2, 3, 4, 5, 6, 1. It is like this, it is mapping this. Okay, now tell me what, so it is clear that you have this one. So pi 1 is this map, this is pi 1, this is the map pi 1. Now tell me, this is some p, this is some, we don't know, let's p1 goes to p2 by this map. Now say, they are saying which are the polygons such that this p1 is equal to p2, like you have colored also. Okay, so can you think of, so 1 2 3 is not like 1 2 3, okay, it is like coloring. So you have some color, let's say white here, white here, white here, let's say black here, white here, white here. Now if you map it, what will happen? Here you have white, white, so at this position at 4, what will happen? This will be black, this will be white, white, white. So is it same? Are these polygons same? Under X, so X says all the polygons are different, we are not thinking of rotation or anything. X is the collection of all the polygons. Is it same in X?
No.
No, na? So so we cannot have, so basically okay, just think of what are all the polygons we could have in this place.
Ma'am, one is a clockwise rotation, all the vertices.
No, we are not changing pi 1. Pi 1 is fixed, we have just rotated by 1, we have just rotated once, that is for sure true. We have
Ma'am,
no
one is anti-clockwise rotation and another is clockwise rotation.
no. We are not changing pi 1. Pi 1 is fixed. We are asking all the polygons such that pi 1 p is equal to p. That is your question. You need to find out all the polygons such that when you apply pi 1 is fixed. That is clockwise rotation by 1. Okay. So pi 1 p, this polygon goes to somewhere when you apply pi 1. Okay. Now they are saying when it is mapped, then it is given the same polygon. When will it happen? So that is your question. You need to find out the polygons. Pi 1 is fixed. For example, if we see like if you have white, and here there is just black, then there will be a problem, right? So basically think of it, you have 1 goes to 2, 2 goes to 3. Think of it like, for example, at the position 1, okay, at the position 1, if you have black, so it should be, so this position, the two positions should be black, right? Now if you like what does that mean? To have the same polygon. So my claim is like that you have just two options. Either you have all white possibility, then it will be same, because if you rotate it you will get again white, because there is no abrupt there is no problem here, like white will go to white. So there will be no problem. This polygon will map to this polygon, which is same. All are white, that is just one polygon, right? So my claim is this set will contain all okay, this set cardinality is equal to 2. Either all the positions are black, or all the positions are white. Just two possibilities are there. Why this is happening? Just think of it. You are rotating and you are asking, you should get the same figure, you should get the same position color. Okay, for that what should happen? One is going to 2. That means if at the position 1, if it is black and it is going to 2, okay. Oh, okay, it's fine. So basically it's fine. I'm just saying I have written it in a, so you have 1 2 3 4 5 6. So I was just thinking in terms of position. You can actually think of 1 goes to 2, that means 1 goes to this position, 2 goes to this, 4 5 6, yes, like this rotation. So now can you think of in terms of rotation? Is that okay?
Yes.
Right? Okay, yeah, I guess this was the confusing part. So 1 goes to 2. So for example, let's say this is black, then this is black and it goes to so this is black, so this place should be black, right? When you rotate it you should get the same thing, right? So that means if you take 2, okay, 1 goes to 6. Now think of where 6 is going. 6 is going to 5, this should be B. Now if you take so this is 5, right? And so just think of what you are getting. Okay, how should I explain it? That is the task. But if you rotate it, if white is somewhere, then if you rotate it you should get the same figure. That means the only possibilities are you have all the places should be white or black. If you, for example, when we have seen, if you have white here, one, so for example black, and you have white here, and if you map it you will get for example, you have rotated once, so you will get black, white will be here, right? So these figures are not same, right? Are these figures same?
No.
No. So that will be a problem. Like if you have any one to be white or more than that, you will be in a problem. Like P will not go to P. This polygon will not go to P. These are not same, right? So only possibility where this will be like you will get it, That is only like if you have all white or all black. So think about it again if that is a problem. And similarly, if you take any rotation, you will get 2 where I is going from 1 to 36. So basically we are saying we will get 2 every time. Just for pi 0 if you have this. Okay, right. So because of this you have your answer that says the number of elements should be 1 mod g, again summation x pi, and pi goes to pi belongs to g. So the cardinality of this is 37. Now x pi 0 plus x pi 1 plus up to and so on, this is your sum. So if you take any rotation, you will be like, you will just get just two polygons which have this thing. So x pi 0, as you calculated, this is this, and this is 2, this is 2, 2 and so on 2, and this is coming 36 times because it's starting by 1 and till 36. So you have your answer to be 36 into 2, that is 72. So 72. So this should be your answer. Okay, so this is this 2 raised to power 37, this one. That is your question. I guess similar questions are in your assignment also, so you can try it like this. Do you have any doubt right now? I can try to explain for sure. Is it
Assignment to first question.
okay? Yeah, last question. I'll just go once. This is very normal. So all finitely generated groups. So it has been asked what are all the options that are true or not. All finitely generated groups are non-commutative. All commutative groups are finitely generated. So just think of. I'll just have an example. It is saying all finitely generated groups are non-commutative. So you have to consider a finitely generated group and it should be non-commutative. So actually you are not dealing with non-commutative groups. So basically just take a finitely generated group. If it is commutative, then this is wrong. So finitely generated group, let's say Z2, right? So if you take Z2, it has just 2 elements. And if you see, it is generated by 1, right? Just 1 element. This is finitely generated. So but and this is abelian group, right? So this is a counter example for this. This is finitely generated by just 1 element, okay? And this is an abelian group, so non-commutative group. For second, all commutative groups are finitely generated. That is not true. So I am just giving an example. You can try it on your own. So Q plus is not finitely generated. Because you cannot take any finitely generated group. When you take it, you add it up and just try it out, you cannot get any so basically so for finitely generated group, as you are familiar now, so you have, when you have addition, you are just saying n1 p1, so it's like power are just like sums, so n1 p1 n2 p2, it's like this. So we are talking about addition, that's why we have to write it like this. And ni's n1 p n2, these are greater than or equal to, or maybe let's say just belongs to z. So this is not finitely, so this set you cannot take some pi's, like some fixed pi's, finitely many elements, so that it will generate the whole group. You can try by this, like if you take 1, you will get 1 plus 1, 1 plus 1 plus 1 plus, so you have this plus 1. So I am giving a generated set much noise outside. So I am saying you just take this 1 by 3, 1 by 5. So you just take primes, and you know primes are infinitely many. So this q plus is generated by this set. So actually this is generated by this set, and you cannot have the lesser number so that it will become finite, because you know primes are infinite. So you have 1, 1 by 2, 1 by 3, 1 by 5. You are taking the prime numbers, and you will have your generating set, but it is infinite. So yeah. So
Z plus is finitely generated.
yeah, z plus is finitely generated. We need to give a counter example. So for counter example, we need to find a commutative group which is not finitely generated, and you know z plus is finitely generated by 1. You just take 1, you will get all the elements, 1 plus 1, 1 plus 1 plus 1. So using this you will, so for example here if you see n into 1, so you will have all the elements, right? Exactly. This is finitely generated, but this is saying this option is everywhere true. Like you take any group, and if it's satisfied that this is commutative, then it has to be finitely generated. So this is not true. That's why I'm giving this example. Q plus is because q in rational numbers, if you sum, like this is a billion, if you sum 1 plus 1 or 1 plus 1 by 2, or you sum 1 by 2 plus 1, you will get the same thing. So this is a
And
billion.
their P1, P2, P3 also, they're not
Yeah, sorry.
they're just
They
numbers.
are yeah, they are just okay. This is confusing, I know. These are just some elements. So in the definition, if you see, we have taken some elements. So it could be anything, like you could say q1, q2, q3. These are some elements, and you are saying that this is generated by this. That means all the elements should be in the direct sum of this, like it should be in the sum of this, or linear combination of this. For example, n1 q1. So in your definition, if you remember, what have we written? We have written q1 raised to power n1. So these are just numbers into qm raised to power nm, where ni's belongs to integers. So these are, so here if you see, the operation is addition. So q1 into q2 means q1 plus q2 here. So whatever operation you have, and q1 raised to power 2 matlab q1 into q1, that means q1 plus q1. So operation is there. So we this is just a like for simplicity, we don't always write star 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 or something. You can definitely use dot, but again it is confused by multiplication. So but whenever we are writing in this group, we are not saying this is multiplication. It is just operation based, okay, whatever operation you have. So here if you see, we have addition. This thing will look like n1 q1 plus up to and so on nm qm, and you have ni belongs to z. Okay, so this is your set. Okay, now you are seeing all the elements you can generate it using this summation. You cannot do that if you take, like for example, 1 1 by 2, 1 by 3, 1 by, yes, you just say 4 elements, then you cannot get 1 by 7 type of thing. Like in the denominator you should have all the primes, right? That was your task. Okay, so that's why you cannot have limited number of elements in q. You are thinking, you are getting my point. If you take finitely many, then denominator is some finite thing. Like if you say you have taken, for example, till 1 by 39, for example, or 1 by let's say 1 by 101, then if you take all the elements you take and then you sum it up, then in the denominator you could have the product of all these elements. Like for example, I'm just giving you an example. You have 1 by q1, okay, q1 is used now. So let's say it is generated by this set. So I'm saying why this is not finitely generated. For example, you have this set, then you are saying this is finitely generated. Then maximum the combination you could have, it's like this. Like you could have all the combination in this set, right? And m by pm. Now if you take the sum this, then you will have the product here, right? You will have the product. Then this is the maximum product you could have in the denominator, but q is not limited. Q could have like p1 p2, because primes are not finite. Prime could be like you can always get next prime, these are infinite. So you will have pm, let's say you have this, then in the denominator you never get this, and this is an element. One by this set, one by this element is an element in q. So you cannot have the finite elements to generate it. Or you could say here like you could take q1, you could take numbers also in the upper part, like in the numerator, but again in the denominator you have finite thing whenever you do. Is it clear why this cannot be finitely generated?
Yes.
Okay, so that's why this is not true, this is not true, so none of the above. Okay, so I'm done with my questions. Now you may ask your question.